Hi, thanks to Keo for the very kind introduction. So good afternoon, everyone. My name is Forrest Huang. Today I'm going to talk about our paper that introduces Sketchforme, a system that would compose sketch scenes from text descriptions. This work was done in collaboration with my research advisor, Canny, at UC Berkeley. So sketches are very widely used in design, art, and engineering. These abstract drawings are used frequently by engineers and educators to materialize their intangible visions and concepts in a graphical manner while being able to discard unnecessary details. And because of this, there hasn't really been a shortage of interactive systems developed by the HCI and graphics research communities, ranging from crowd and sketch-based UI design tools to automatically generated sketching tutorials. On the other hand, synthesizing graphical content has gained a lot of attention in the machine learning community, especially thanks to the development of deep neural networks, deep neural-based generative models that improve the quality and variety of generation. So in this work, we combine a text-based image synthesis technique that is able to synthesize layouts from text descriptions and a generative model that's able to sketch individual objects to automatically generate sketches in various interaction scenarios in hope to spread the benefits of sketching to diverse applications. So our main contribution here is we developed the first neural network-based system that automatically generates complex sketch scenes based on natural language descriptions. So let's jump right into how exactly did we achieve this goal. So to generate a sketch, as we see in our workflow here, we decompose the generation task into two stages in Sketchforme. So when a user provides a description, such as a horse under a tree, we pass the description to generate a scene composition, dictating positions and classes of various objects in the scene. And then taking this composition, our object sketcher generates the intended sketch strokes from the object properties and composes them into the scene. So before we move on, I think this is a great opportunity to summarize our technical innovations here. First, we contribute this two-stage framework alone for sketch generation. Second, it's a transformer-based layout generation model. And finally, we introduce a ratio condition to control the sketch generation model in our two stages of Sketchforme. Now, let's start with the scene composer. Sketchforme is a data-driven and machine learning-based system. So before we start building the model, let's look at our data sources. Where do we learn this knowledge? So the big problem is, unfortunately, large-scale text-to-sketch direct mapping dataset is not available until this day. But since all we need is composition data, we can learn this from natural images, which has datasets that are widely available. So we use the visual genome datasets that are densely annotated, consists of objects, relations, and text descriptions. And we took the commonly occurred 100 objects, 70 predicates in our data set, and produced about 102,000 instances for training, validation, and test of these object relations. So here is our scene composer. So to generate these relations, first we take the natural language description, tokenize it, pre-process it through glov vectors to get a semantic representation of each of the text tokens, and encode it using both a transformer encoder and an LSTM encoder for two streams in the generation process. And so for the first transformer stream, we decode it with a transformer decoder, which, putting this into context, outputs just the coordinates of the bounding boxes. And then we also have the LSTM decoder that outputs the class labels, which tells us what class of objects does the object boxes belong. So we repeat this process for each bounding box, and in this case, after we generate the horse, we also generate the tree behind it until we see an end token that's generated, because both transformers and LSTMs is a sequence model. So this is how we generated our scene, but how do we exactly do in this task? What's the performance? It's a little bit hard because these generative models can be hard to evaluate, but one good thing about our bounding boxes is we can actually visualize it. So we take a look at the boxes generated by our models. We separate each object out for easy visualization. And one thing to note that is our model actually has a Gaussian mixture model front end that lets us generate slightly varied bounding boxes from the descriptions, because if you think about each text description can represent slightly different bounding boxes that follows a certain pattern. So we superposition these boxes and combine them into a heat map that shows the distributions of generated boxes. Now, we compare this generation boxes with, we produce these heat maps using the same process as what the bounding boxes in the data set, and we compare them. Now, this text description is slightly sparse in the data set, so it's a little bit hard to compare about them. But if we look at ones that are more densely populated in the data set, we can see that they generally exhibit similar distribution patterns between the data sets and our generations. Now, this is only a visual way of looking at these bounding boxes, but we have a more quantitative metrics that describe in detail in our paper. So if you're interested, please feel free to read our paper. So this is our scene composer. And now, after we generate the scene composition, let's turn it into actual sketches using our object sketcher. And once again, let's look at the data set that we can use. In this case, since we only need individual object concept classes, we actually have data set for that. So for individual sketch objects, we take the quick draw data set that you might have heard of as a game developed by Google. It's the first large-scale sketch object data set that has around 345 concept classes and around 80,000 instances per class run by human users in 20 seconds. Now, this is actually not enough to compose these sketch objects into our scene, because these sketches in this data set is actually just classified in a very high level categories, like just trees, all kinds of trees. But there's no fine-grained descriptions for poses within a subclass, or even the aspect ratios of trees. And you can see why this can be a problem. Sorry, the bounding box is very blunt here. So. You can see the tree here, it's actually quite wide and kind of boxy. But if the model, if we don't give guidance to the model to generate a specific kinds of tree, it can give like a very thin tree that might be inappropriate to compose them into the scene. So we need a mechanism to actually control the aspect ratios of the sketches. So we took the existing SketchRNN model that comes with, that's introduced with the quick draw data set, which is a quite basic next stroke prediction model. And we actually introduced this novel aspect ratio condition, which we can actually compute analytically from the training data. So we take each of the sketches and we take delta y and delta x, and we get a ratio, and we pass in as an additional condition to each generation step for each of the strokes. And now, given these ratios, we can generate a lot of trees following their aspect ratio. So each of the rows are different trees generated with the same aspect ratio. And as we move down the rows, we can see as we increment the ratio, which we should observe taller trees as the ratio gets higher. And we actually see this pattern here. Now, this is not pixel perfect, but then it's quite good enough for our purpose. So this is the object sketcher of our system. Now, let's look at some generated sketches that comes out of our Sketchforme system. So these are some complete sketches generated by Sketchforme. We can see that each object are adequately placed in the scene despite having slightly different, they all position slightly differently or have slightly different sizes, but they all follow the patterns that dictated by the descriptions, like a boat under a bridge and a dog on top of a car. And for here, we have a bike next to a bench where both of these objects are placed almost at the same altitude in the scene. And finally, we also have an apple on a tree where you can see that the apple is not actually put on top of the tree, but it's like stemmed out almost from the leaves, where it's able to take these contexts into account. And on top of these simple scenes that we get from Visual Genome, I want to show that our framework can still generalize to recognize multi-object spatial relations and more abstract concepts in the data sets with more objects. And this is trained on a data set with more objects but more densely combined data set. So in this case, we can see the model can recognize abstract concepts such as living room and place couches and houseplants in the scene. And more than just visually inspecting our generations, we actually perform the human perception test on each of the sketches. On Mechanical Turk, on 51 users, we take 50 sketches across 5 descriptions, half generated by human users, half by Sketchforme. We actually have 10 for them to actually train before they rate each of the sketches. And we ask them 2 questions. The first is Turing-style test, probing the realism of the sketches. And the second one is a 5-point Likert scale question, asking them how well did the sketches convey the message. So for both questions, actually, human-generated sketches perform significantly better than Sketchforme-generated sketches. For the first questions, the human-generated sketches are considered more realistic, and when we dive into why exactly is this the case, a lot of users reported that there's much more jitter in the human-generated sketches, as you can see in the examples. So and the Sketchforme-generated sketches are way smoother. So if realism is a concern, we recommend future work to actually model the stroke variations or even do adversarial training if it is a concern. And for the second question, Sketchforme performs way closer to humans. They have more similar ratings. And it's actually significantly better for 2 of the 5 descriptions that we present them for rating, which shows the competitive performance of Sketchforme in some cases in communicating the underlying message of the sketches. So now we have developed Sketchforme, we've described the system. What exactly is the system good for? What do we do with it? I said we had interactive applications in our title, and I have to mention a couple things about it. So the first applications we built and developed extensively is a Sketch augmented language learning tool, a rather basic one. But this is almost like a flashcard-based learning system where you have a translation in German where you have to select a correct translation in English from a number of choices. So we conducted another between subject user study with 38 participants on Mechanical Turk as well, on 2 sets of 5 English-German translations. And for each of these translations, we split the task into a training and test phase, and the users have to correctly translate all phases in the training phase before they proceed to the testing phase, meaning they are familiar with the descriptions. In the testing phase, they have only 1 chance per description, and they're not shown the sketches in any cases. And to have the participants actually get to see the sketch in the training phase. So what we found is, while there is no significant statistical significance for the correctness of the test phase performance, that users that get the tool with sketches take significantly less time, and they consider the sketches to be more helpful for the task, rating 4.6 out of 5. And this shows the potential of Sketchforme in supporting a language-based learning task. And moreover, we built a sketch assistant prototype that can auto-complete user sketches based on their preferences. And this is less evaluated, but more of like a prototype application. So we can see, so this is instead of system-generated sketches, the user-provided sketch. Given the description and the user-provided sketch, we can auto-complete the scene. And on top of that, because we can generate a variety of scenes, we can actually show all of them to the user and ask them to pick the favorite one. So this is a step closer to a more collaborative human-in-the-loop machine learning system for doing iterative sketching and drawing tasks. So towards the end of this talk, I want to point interested researchers to a couple directions of future work that we think is worth pursuing. First is developing a conversational system instead of a one-shot sketching paradigm that Sketchforme implements in this case, as like a conversational environment might more closely resemble to the sketching process, iterative drawing process, or even the creative process or design. The second part, we recommend investigating coloring and animations for these sketches because these natural images might be able to be used for coloring data. And we also have these like densely annotated video data sets that's recently published. So maybe we can actually learn these animations poses from the video data sets. And finally, we're looking into applying Sketchforme on education in other domains, especially in those cases where sketches is not an assistive purpose from a language learning application, but serves as a functional purpose like mechanical engineering or industrial design. So to conclude, we introduced Sketchforme, the first neural network-based system that automatically generates complex sketch scenes with multiple objects from natural language descriptions. We factor the complex sketch rendering task into layout generation and ratio condition object rendering subtasks performed by our scene composer and object sketcher in Sketchforme. So with that, I thank you for your attention, and I'm happy to take questions from the floor.
Yeah, please.
Thank you for the great work.
No, sorry. Look back.
Thank you for the great work. I'm curious whether have you evaluated how creative this tool is? For example, have you compared your output with your data set, whether it is like directly from the data set or simply interpolation of the data, or it's like not similar to any data, but it's still meaningful? Thanks.
Cool. Thanks for the question. So the question is whether it's an interpolate, whether it's how creative this the system actually is, whether it represents some examples from a data set or is more meaningful. So I guess we didn't directly evaluate it because even creativity is very hard to quantify, right? Because as you say, but I would say one thing to keep in mind is because it's a data-driven system, it's only going to be as good as what the data gives it. So the amount of interpolation is it would be obvious for some cases, but we actually did look at some cases where there are no such descriptions appear on the data set. Like I believe in the paper we actually have a cat on a horse, where there's actually none of these in the data set, and it actually does generalization okay. And we also see that from, because when we train the model, we look at the training performance and the validation performance. And obviously, if it overfits the training set, then it might be memorizing some examples, but we make sure that doesn't happen when we train the model, because we have to have a robust model, we should have the training set and the training loss and the validation loss to be low. So, but I would say how creative it is, I think in terms of like a rather naive measure, it's probably okay from what I've just said now. But I think being creative is a very large question. And I also think the system is not like a complete solution. Like it's not like it's the end of the story. I think if you're looking for creative purposes, I think these systems are only mostly good for giving inspirations. I think humans should be in the loop to generate interesting sketches.
So we have one more question.
Right. Tetsuya Sakai from Waseda University. Great talk. So you showed us an example about a horse under a tree.
Yes.
Right. Can you handle a horse behind a tree? More generally, so what are the limitations, regarding the kind of natural language queries that you can handle?
That's a very great question. So I think the horse behind a tree, if you look at our paper, we actually mentioned that's like a very significant limitations of our model, because right now we don't explicitly model the layer orders. It's mostly just the order it's mentioned in the description. So occlusions is a very big problem, even if it's not explicitly behind or in front. If it's just placed on top of each other, there would be issues on that. So one thing you can do is to create another model that models occlusions from natural images. That's possible. The other limitation we see is even with the ratio condition that I mentioned, you can think about the same ratio can also have like horses facing left or facing right. So post-aliasing is a problem given just the ratio. So we actually are actively developing that. And to move forward, there are two things we are thinking about doing. The first thing is using an object mask, the entire mask, instead of just like an aspect ratio, which gives a more better representation of the object pose. And the second one is actually having a continuous representation of objects instead of just like one hot label and also the aspect ratios.
Okay, thank you. So we thank the speaker, and then let's move on.
Thank you.